During a tennis serve, a racket is given an angular acceleration of magnitude 175 radians per second squared at the top of the serve. The racket has an angular speed of 17 radians per second. If the distance between the top of the racket and the shoulder is 1 meter, find the magnitude of total acceleration. All right. Total acceleration top of the racket. All right. First thing we're going to do is draw a picture. So I'm going to represent the top of the racket as a block. I know it sounds pretty abstract, but we're going to go with it. And it's moving in a circular arc, like so. And this tennis racket, this tip of the tennis racket, the top, is going to have two types of acceleration. It's going to have acceleration tangential, and it's going to have acceleration centripetal towards the center. And we are given that the acceleration tangential, AT, is 175 radians per second squared. And then we're also given an angular speed. So what we want to do is set acceleration tangential. So a velocity has two components. It has both a magnitude and direction. And acceleration tangential, what that does is it's changing the magnitude of the velocity. It's speeding up the way we traditionally think of speeding up as. The other part of velocity, not the magnitude, but the direction, when we change the direction, that's going to be due to centripetal acceleration. That's why you have centripetal acceleration when you're moving in a circle. When you're moving in a circle at a constant speed, you're actually accelerating because you're changing the direction of your velocity vector. Whenever you have a change in velocity, that's going to be an acceleration. So we have to take both of these into account. So we already give us centripetal acceleration. Acceleration centripetal is just acceleration with a little c below it. The subscript just tells me that it's centripetal. So we're going to have v squared over r, which r is radius. That's going to be the length of the arm. And now we want a relationship between linear and angular. So the relationship we're going to have, whenever you have something that's not slipping, whenever you see these are moving together, so it's going to be the same as if it was rolling without slipping, which is kind of a key phrase you see. R equals R alpha. These are actually a cross product, but for this case, since they're moving in a circle, I'm going to write these as just x equals R alpha, or R theta, v equals R omega, and a equals R alpha. So for this one, what's going to concern us is the second one right here. Now, we can rewrite this as, oh no, we don't have to rewrite it. So we just plug it straight in. So v squared is going to be r squared omega squared. I know sometimes you use capital R, sometimes you use lowercase. I should be more consistent. I'm not. I'm sorry. Part of life. Oh, not squared. There we go. One of the squares cancel and get omega squared r times radius. So now, since we know it's speed, we know it's radius, so we're going to get acceleration centripetal equals the angular speed, 17 squared, times radius, which is 1, which gives us, let's see here, go to my calculator, 17 squared is 289. So there, that's going to give us 289 radians per second squared. We are going to convert that over to, we're going to combine vectors now. So we have acceleration centripetal, acceleration tangential, acceleration centripetal. Some say also radial, same idea. And so we're going to have 175 plus the vector that's perpendicular, because these are perpendicular, 289. Add those together vectorially. We have 175 squared plus 289 also squared. Then we're going to square root the sum of those, and we get a hypotenuse of about 337. 0.8, 0.9. And so the answer then is going to be 338 radians per second squared. That's supposed to be an S, but they want it in the total acceleration, which I'm going to assume that they mean linear, not angular. Because if they wanted angular, they probably would have said total angular acceleration. It doesn't matter. We're going to convert it over to linear, and the conversion factor is right here. A equals R alpha. We have alpha. This is alpha right here. The total, A total angular acceleration. So we need to multiply it by R, the radius. And so the total acceleration, A total, is just going to be 338 radians per second squared times a radius of 1 meter. And then that's just going to give us 338 meters per second squared. So the idea with this one is that when you have the total acceleration that you're feeling, that the top of the racket is feeling, is both due to how the racket's going increasing speed, but also that's moving in a circular motion. Circular motion is also causing an acceleration. So, hope that one helped. See you on the next problem.